All right, let's dive into a topic that honestly trips up so many students, but is absolutely essential for every single physics calculation you'll do: significant figures. Getting this right isn't just about being precise, it's about making sure you secure every single possible mark on your exam.
Hello, NEET aspirants. Yep, this one is especially for you. We're going to break this whole thing down so you never ever lose a mark on it again.
So, here's our game plan. We'll kick things off with the basics, what these things even are. Then we'll get into the core rules, tackle the tricky exceptions, and of course, master the math for your calculations. We'll wrap it all up with a quick summary to make sure it's locked in for exam day. Let's get right into it. Let me ask you something. Have you ever had that super frustrating moment where you've done all the hard work, you've solved a really tough physics problem perfectly, but your final answer gets marked wrong just because of some tiny difference after the decimal point? It's the worst, right? Well, that is exactly what significant figures are here to prevent. Section 1. What are significant figures? So, what's the big deal with these things anyway? Well, you can think of them as the language of precision in science. The textbook definition is actually pretty simple, but it's really powerful. Significant figures are all the digits in a measurement that you are absolutely sure about. We call those the reliable ones, plus one and only one estimated or uncertain digit. It's how we communicate how good our measurement is. Let's make this real. Imagine you're in the lab, you time a pendulum swing, and you get 1.62 seconds. Now, you're totally confident about the 1 and the 6, but that last digit, the 2, that's your best guess, right? It could be a little more, a little less. That's your uncertain digit. So you've got 2 reliable digits plus 1 uncertain one, giving us a grand total of 3 significant figures. Okay, now for the really practical stuff. Section 2, the rules for counting. Because before you can use them, you've got to know how to spot them. These 5 rules, they are your absolute foundation. Here they are in a nutshell. Any digit that isn't 0, it's always significant. Zeros that are trapped between non-zero digits, they count too. Now, zeros at the very beginning are just placeholders, so they're out. And for the tricky ones, the zeros at the end, it all comes down to one thing. Is there a decimal point? If there's no decimal, they're not significant. But if you see a decimal point anywhere in the number, they absolutely are. All right, now let's tackle the part that really messes with people's heads. Section 3, handling ambiguity and exact numbers. Pay close attention because these are the special cases you absolutely have to know for your NEET exam. Check out this classic problem. You have a measurement of 4.700 meters. Based on our rules, those trailing zeros after the decimal mean this has 4 significant figures. Simple enough. But what happens when you convert it to millimeters? It becomes 4,700. Uh-oh. Suddenly it looks like it only has 2 significant figures. We lost precision. This is a huge problem. It's totally ambiguous. So how do we solve it? The solution is actually super elegant and simple. Scientific notation. By writing a number in this format, a times 10 to the power of b, we get rid of all the doubt. And here's the crucial part to remember. The power of 10 part has absolutely nothing to do with counting significant figures. You only, and I mean only, look at the base number. And this is where scientific notation just saves the day. If your measurement was only precise to 2 sig figs, you'd write it as 4.7 times 10 to the 3. But to show that original, super precise measurement with 4 sig figs from 4.700 meters, you write 4.700 times 10 to the 3. Boom. The precision is crystal clear. No more ambiguity. Okay, another special case, exact numbers. Now, these aren't measurements from a ruler or a scale. They're definitions. Think about the formula for a circle's circumference, 2 pi r. That 2 isn't around 2, it's exactly 2. It's like 2.000 with zeros going on forever. So what does that mean for you? It means an exact number will never be the weakest link that limits the precision of your calculation. Okay, deep breaths. This next section is where all your hard work really pays off. Section 4, rules for calculations. This is literally where marks are won or lost on your exam. Listen up, because this is a massive NEET exam tip. There are 2 totally different rules, and you cannot mix them up. For multiplication and division, your answer is limited by the number with the least number of significant figures. But for addition and subtraction, you switch gears and look for the least number of decimal places. Mixing these 2 up is probably the #1 mistake people make. Let's see it in action. Say we're calculating density, which is mass divided by volume. The mass has 4 sig figs, but the volume only has 3. Okay, so 3 is our weakest link. That means our final answer must also be rounded to 3 significant figures. So that long number your calculator spits out, 1.68804 and so on, it just becomes 1.69. Simple as that. Now let's switch over to addition. We're adding 3 masses together. Here, we totally ignore the total number of sig figs, and we only look at the digits after the decimal point. The values have 2, 1, and 3 decimal places. The least is 1 decimal place, right? From that 227.2 grams. So our final answer has to follow that rule. It must be rounded to 1 decimal place, giving us 663.8.
We've just seen how critical rounding is, so let's make sure we've got it down pat. Section 5, the art of rounding off. This is the final polish that gets your answer exactly right. Okay, rules 1 and 2 are the easy ones you already know. If the digit you're dropping is bigger than 5, you round up. If it's less than 5, you leave it alone. But what happens when the digit is exactly 5? This is where a clever rule comes in. You always round to make the preceding digit an even number. So if the digit before the 5 is already even, like the 4 and 2.745, you just leave it. If it's odd, like the 3 and 2.735, you bump it up to become even. It's a neat little trick to prevent statistical bias over lots of calculations. Notice how both examples end up as 2.74. And here it is, a golden rule for your exams. Never, ever, ever round off in the middle of a problem. If you do, these tiny little rounding errors start to pile up and your final answer will be off. The pro move is to keep at least 1 extra digit throughout all your intermediate steps and only apply these rounding rules once, right at the very end on your final answer. Phew, we have covered a ton of ground. Let's boil it all down into a final revision checklist. Section 6, Summary and Key Exam Takeaways. So, let's recap the absolute must-knows. Significant figures are all about communicating precision. If you're ever in doubt, use scientific notation to avoid ambiguity. Remember the 2 different calculation rules. It's least significant figures for multiplying and dividing, and least decimal places for adding and subtracting. Exact numbers, they have infinite sig figs, so they're never your problem. And most importantly, only round at the very, very end. This slide right here is your cheat sheet.
If you found this video helpful, please like, comment, and subscribe for more physics content.